Thanks very much, Chris, and thank you very much to the organizing committee as well. So the talk will be divided into 5 sections. First, we'll be introducing a particular concept of reduction as domain subsumption, then how to strategically or methodologically approach questions of domain subsumption between theories in physics. Then I'm going to give some examples. Then I'll talk about the relationship between this particular concept of reduction to between it and emergence and universality, and then I'll briefly wrap up. So we're all here to, in some sense, address the question, right? What relationship should any theory of quantum gravity bear to the standard model and general relativity? Presumably, one aspect of this relationship includes domain subsumption, right? That the domains of validity of the standard model and general relativity are both strictly contained in the domain of validity of quantum gravity. Right, so I'm just taking, right, so there are many meanings assigned to reduction, right, and domain subsumption is one particular meaning that's often implicitly associated with usages of the term reduction. Right, and we'll define the particular concept of reduction that we'll talk about here. And now it's helpful to distinguish between concepts of reduction and approaches to reduction. Right, so philosophical accounts of reduction, like limit-based reduction or Nagel-Schaffner reduction, can either be taken as defining their own concepts of reduction, right, or as approaches to reduction in some other sense. Right? So for example, as approaches to reduction in the sense of domain subsumption. Right? So the concept of reduction that we're going to be talking about here, right, is not fundamentally defined by the requirement that one theory must be extracted as a mathematical limit of another, or fundamentally by the requirement that one must be able to deduce the laws of one theory from another. Right? However, right, we leave open the possibility that limits and derivations a la Nagel, right, may be useful approaches to reduction in the sense that we're interested in here, right, which is domain subsumption. So what does it mean precisely for one representation of a system or a set of systems, like a theory or a model, right, to subsume the domain of validity of another? Right. Now, the definition I take here is that, right, the set of contexts, right, where one representation is approximately true is strictly contained in the set of contexts where the other is approximately true, and the margin of approximation characterizing the approximate truth of one, right, is no larger, right? So the margin of approximation characterizing the approximate truth of the reducing theory, right, the more fundamental in a sense, right, is typically no larger than the margin of approximation characterizing approximate truth of the reduced theory or model. Right, so this definition of domain subsumption falls back quite heavily on the realist's notion of approximate truth here, and so we'll assume a certain realism. Right? So the rest of the analysis will fall back on scientific realism or on a realist picture. Right? And it remains to be seen to what extent it can be carried over to a more empiricist picture. Now it's worth noting here that domain subsumption can also be understood in an empiricist sense. Right? For example, in the sense defined by Kameny-Oppenheim reduction, right, which requires that all observational data that are explained by the reduced theory are also explained by the reducing theory. Right, but we're not going to be taking this empiricist understanding of domain subsumption. We're going to be taking a more realist approach. Okay, so now I'm going to discuss questions about the methodology of domain subsumption in physics. And in order to do that, it will be helpful to draw 3 distinctions. Right, so first, between formal and empirical approaches to reduction. Right, so formal approaches to reduction treat reduction as solely a question of the mathematical relationship between the theories. So basically, they proceed on the assumption that one only needs to know the mathematical models or the mathematical framework of the theory in order to assess whether reduction occurs. Empirical reduction incorporates also empirical input beyond the mathematical frameworks of the theories or models, right, in order to assess, right, whether one reduces to the other. It's also useful to distinguish between global and local approaches to reduction. So global approaches require a single universal derivation of the reduced theory's successes. Local approaches allow for many or multiple context-specific derivations or explanations of the reduced theory's successes. Finally, it's worth distinguishing between theory-based and model-based approaches to reduction, a distinction which is closely related to the global versus local approach. And theory-based approaches focus primarily on the general features or axioms that define the theory as a whole, whereas model-based approaches focus on the more kind of narrowly tailored specifications that concern relations between models of a single system. Okay, so in approaching questions of domain subsumption, right, one general idea, right, is to identify structural and methodological commonalities across different theory or model pairs in which one theory subsumes or is thought to subsume the domain of the other. Right, so we want to look at various inter-theory or inter-model relations across physics and hope to find some clues about how to constrain quantum gravity on the basis of current theories like the Standard Model and general relativity. Now, I'll be looking at two particular ways of executing this idea. Right? The first is limit reduction, which attempts to demonstrate domain subsumption by showing that one theory is a mathematical limit of another as some parameter approaches 0. Right? And so this is one variation of this is Nichols's reduction 2, and it's also, as we'll see, exemplified by what's known as the Bronstein Cube of physical theories. An alternative approach, which attempts to build on a suggestion by David Wallace, right, is what I'll call proxy reduction. Right? And it attempts to show that the mathematical structures of the more encompassing theory approximately instantiate the structures of the less encompassing theory in context where the less encompassing theory furnishes an approximately true representation of some real physical system. Right, so just as illustrations of these two approaches, I'll give you two quotations, one from Michael Berry and then one from David. Right, so I'll read the quotation from Michael Berry first. So the less general theory, so this illustrates limit reduction, or one way of formulating limit reduction. The less general theory must appear as a particular case of the encompassing one as some dimensionless parameter, call it delta, takes a particular limiting value. A general way of writing this scheme is encompassing theory goes to less general theory as delta goes to 0. Thus, reduction must involve the study of limits, that is, asymptotics. The crucial question will be, what is the nature of the limit delta goes to 0? We shall see that very often reduction is obstructed by the fact that the limit is highly singular. And this is an idea that's also been put forward by Robert Batterman. Wallace, on the other hand, writes, the instantiation relation, I claim, is the right way of understanding the relationship between scientific theories, the sense in which one theory may be said to, quote, reduce to another. Crucially, this reduction on the instantiation model is a local affair. It is not that one theory is a limiting case of another per se, but that in a particular situation, the, quote, reducing theory instantiates the, quote, reduced one. And so, this is just a brief quote from the Emergent Multiverse, but it's an approach to reduction that I think deserves a name, right? And it deserves to be developed and fleshed out a bit. And so I will call it here proxy reduction, and the reason for this name is essentially that we look for some surrogate or proxy, right, in the reducing model of the mathematical structures, the empirically salient mathematical structures in the reduced model. And so so I have two core claims here, really. The first is that the most appropriate strategy for reduction in the particular sense of domain subsumption is local, empirical, and model-based. Right? And the second claim is that domain subsumption is grounded in a particular type of empirically constrained mathematical relationship between two models that describe one and the same system. And so often we can have many models of a single physical system. Right? And so this empirically constrained mathematical relationship, right, ensures that mathematical structures of the reducing model approximately instantiate the structures of the reduced model in those contexts where the structures of the reduced model are approximately true, or furnish an approximately true representation of the system. And so as I'll attempt to show briefly, although I won't have too much time, this general type of relationship, which I'll first describe in general terms, is exemplified by many intermodal relations in physics. Okay, but first I want to briefly discuss limit reduction, and one way of attempting to map the relationships between various established theories in physics. And the manner in which the Bronstein Cube attempts to map relations between these different theories is via taking limits of constants of nature. So along one axis we have h bar, or Planck's constant. Along another we have the inverse speed of light. And along a third we have Newton's gravitational constant. Right? And the idea here is that Newtonian gravity, for example, if we look along the very back axis, right, should approach classical mechanics and the limit g goes to 0. Right, so for example, special relativity, right, should approach classical mechanics, right, understood as Newtonian mechanics, and the limit where 1 over c goes to 0 or c goes to infinity. Right? Quantum mechanics should approach classical mechanics as h bar goes to 0. Right? So this particular approach to mapping the relationships between different established theories in physics relies on taking limits of constants of nature. Right? And this is a view that's been criticized by several authors, notably Jeremy Butterfield in his 2013 talk for the first of these conferences. And so I'll just briefly list here a number of criticisms, some of which have been made by other researchers, and some of which I present as novel. The first criticism, which is probably the most obvious one, is that in the context of real systems, constants of nature are fixed. Right? So physical transparency, right? So if we want to interpret these limits, right, it's necessary that these results be reformulated in terms of dimensionless parameters, right? That we find some physically variable quantity that we can compare to the constant of nature, right, of the same dimensions as that constant, in order to assess, right, which values of for which values of that variable quantity, right, we have the required reduction. But as a matter of practice, right, many analyses simply take the limits of the constants of nature without actually identifying this dimensionless parameter or this dimensionless quantity with which the constant needs to be compared. Another critique is vagueness, right? So which parts of the reduced and reducing theory, so I'll call the purportedly reducing theory the low level, so it's just T sub L, and the reportedly reduced theory the high level, so it's T sub H. And so which parts of these theories are required to converge in the relevant limit? Right? And does any formal limiting correspondence suffice for reduction in this sense? Another critique, right, that's been made by both Butterfield and Hassenfelder is that the limits in the diagram, in fact, don't commute. Right? So if one goes from quantum, if one goes from quantum field theory to classical mechanics, one can do that, right, either via quantum mechanics or via special relativity. So it's often pointed out that many of these limits don't commute. Okay. But I don't want to focus on the specific reasons here just for lack of time. But another objection, right, is that the G goes to 0 limit of GR is not strictly speaking special relativity, as the diagram suggests, right, because of the possibility of non-trivial vacuum solutions. Right? So we can take G to 0 and there still exists in Einstein's equations non-trivial vacuum solutions. And there are similar concerns about the H bar goes to 0 limit. And finally, right, so this is a different sort of criticism, is that limit reduction is implicitly a formal approach to reduction, right? So it presupposes that reduction is solely a matter of examining the relationship between the mathematical frameworks of the theories, right? And and whether reduction holds can be assessed solely through an analysis of those mathematical structures. Right? I argue here that for the particular sense of reduction as domain subsumption, right, a formal approach, right, which pays attention only to the relationship between the mathematical structures is inappropriate, because we also need to pay attention to how our models actually describe real physical systems, and in particular with what degree of accuracy and over what time scales and so on. Okay, so proxy reduction, right? So this is a development of David's idea of reduction as instantiation, right? Reduction between theories T, I will define in terms of reduction. So reduction between theories, which I call reduction T, I'll define in terms of a more fundamental concept of reduction, which is a concept of reduction between two models that describe one and the same physical system. So theory TH reduces sub T to theory TL if and only if for every system K in the domain of TH, that is for every system whose behavior is accurately represented by some model of TH, right, there exists a model of a low-level theory, right, that also represents that same system, right, such that MH reduces sub M to ML, right? So the relationship reduction between theories relies on a specific notion of reduction between two models that describe the same physical system. Right? And so reduction M is defined as, so model MH, the high-level model, reduces sub M to the low-level model with respect to a particular physical system K, if and only if, in all circumstances where MH accurately represents the behavior of the physical system, right, ML furnishes at least as an accurate a representation of K and also represents K's behavior in contexts that are not accurately represented by M sub H. Okay, so here, right, just to define terms a little bit more precisely, right, so any system in the domain of a theory is described by a particular model from that theory. Right, and a model here is understood in a pretty parochial sense, right? So it's just as an assignment of some state space to some degrees of freedom of the system. And typically that state space can either be a vector space or a manifold. The model has also specified constraints defined over that state space, right, which I'll just designate. So it's some relationship, so we'll just say f of x equals 0, so it can just be put in that form, which typically will be associated with the equations of motion or various transformation properties of states in the state space. Okay. So as a shorthand, I'll just write, or I'll designate the model as consisting of the state space and then whatever constraints f we have over that state space that specify the dynamics. Okay, so just to illustrate the particular approach to reduction that I'm advocating here, right, I want to specify a particular class of models. Right, so imagine a case in which we have two dynamical systems models that describe one and the same physical system. Right? And they may describe different degrees of freedom, right, but the state space, the degrees of freedom described by the high-level state space, right, should supervene on the degrees of freedom described by the low-level state space. Right, and the idea here, right, is that we have, right, reduction requires us, or there's a pattern that one observes across many distinct intermodal reductions in physics where, right, one identifies a particular function of the low-level state that instantiates approximately the dynamics of the high-level model, right, within a particular subset of the low-level space. Right, so as long as the state remains in this particular subset of the low-level state space, right, the dynamics induced on the high-level state space via this function, right, will approximate the dynamics of the high-level model. Right, so this function, or a particular function of the low-level state, approximately instantiates the dynamics of the high-level model. Right. And the degree to which it must do so in order for reduction to occur, right, is specified empirically and depends on the degree of accuracy with which the high-level model describes the system itself. Right? So we require the induced trajectory, right, the low-level model's instantiation of the approximate instantiation of the high-level dynamics to approximate the high-level dynamics, or a solution to the high-level dynamics, within some margin of error delta, which is empirically determined and which characterizes the degree of accuracy to which the high-level model actually describes the system itself. Right, so we want the low-level model's proxy or surrogate for the high-level state, right, to approximate the high-level model's description of the system within that degree of freedom, or within that margin of error within which the high-level model actually describes the system itself. Right, so this dl of xl of t, right, is just a dynamical evolution, the low-level dynamical evolution within a particular subset of the domain B. Right, this B is just the function that maps from the low-level state space to the high-level state space, which identifies a quantity in the low-level model that approximately instantiates, right, the structures in the high-level model. Right, SL and SH are just the state spaces, and DH of BXL of T right there is just the high-level dynamics applied to a particular point in the high-level state space that's mapped up from the low-level state space. Right. And so what I'll argue here is that this sort of pattern of reduction, this mathematical relationship, can be extended quite widely to many reductions in physics. Okay. In particular, one way of showing that this holds is to show that the low-level model's instantiation of the high-level structures, right, so this particular function of the low-level state, B of XL, I'll call it, approximately obeys the high-level equations of motion by virtue of a particular restriction to the subset of the low-level state space, right, and the low-level dynamics. Right? So in many cases, one can show that a particular function of the low-level state, right, approximately satisfies the high-level equations of motion. Okay? And it does so for as long as the low-level state remains within a particular subset of the low-level state space. If the low-level state remains within this particular subset, right, which is defined by the requirement basically given here, but that the this function obey the high-level dynamics, as long as, right, so we want basically the time scale over which the low-level state remains within this particular subset of a low-level state space to be at least as large as the time scale on which the high-level model actually describes the behavior of the system itself. Right, so we want, right, the low-level model's instantiation of the high-level structures to approximate, right, the high-level dynamics in those cases or over that time scale where the high-level model actually works. Right, so this sort of approach can be generalized, right, beyond dynamical systems. So generally speaking, right, it's often the case that a model of a physical system will be specified by a state space and some mathematical constraints over that state space, which either consist of a vector field or equations of motion or some sort of tensor structure. So if we're given two models of the same system, right, a high-level model and a low-level model, right, in the high-level theories domain, we require that for every physically realistic solution, right, of the high-level model, right, there exists a physically realistic solution of a low-level model such that they agree, right, such that the trajectory on the high-level state space induced by the low-level solution approximates the trajectory, right, approximates the high-level trajectory within an empirical margin of error delta, right, that characterizes the precision with which the high-level model describes the system itself. So basically, we want the low-level model's proxy or substitute or surrogate for the high-level state to approximate the high-level state in those cases where the high-level solution is physical, right, where it really describes the system. And the function b, it should be noted, just as I said before, right, expresses the manner in which we think the degrees of freedom described by the high-level model supervene on the degrees of freedom described by the low-level model. Right, so in practice, right, this approximation or this dovetailing of high-level solutions with solutions that are induced, right, via this function b by the low-level solutions, right, so this dovetailing, right, often follows, right, from showing that the low-level model's instantiation or proxy for the high-level state approximately obeys the high-level equations or the high-level constraints. Okay. So the idea is just to show, right, so that's just what this equation indicates, right, that the low-level model's proxy, right, approximately satisfies the equations of the high-level model, right, for all low-level states within some restricted domain D. Okay. And it does so by virtue of the low-level physical constraints. Okay. So I spell this out in more detail in a forthcoming paper. Okay, so this has all been quite abstract, and it's maybe hard to see exactly how it applies. So I hope to make this pattern of inference, this pattern of establishing relations between two models of a single system more concrete and to show how it applies in real physical cases. So if we look at a relationship between quantum and classical models of a single system, so for example, if we take a baseball or the moon or a charged particle, and we entertain the possibility, right, that every classical system is also a quantum system and is actually more accurately regarded as a quantum system, right, then we can give two models of this system. Right? The classical model, right, the state space will consist of say classical phase space, and the dynamical constraints will just consist of Hamilton's equations. Say just for argument's sake, it's just the usual p squared over 2m plus v Hamiltonian. The quantum model, right, or the most complete quantum model of the system K, will take into account its interaction with its environment. And so the total state space will be the Hilbert space of the system tensored with the environment Hamiltonian, right? And the dynamical constraints will just be given by Schrodinger's equation with the same Hamiltonian. Right? And so this Schrodinger equation, right, just consists of, right, a system Hamiltonian plus the identity on the environment plus the identity on the system plus an environment Hamiltonian plus an interaction Hamiltonian, which is how decoherence-based analyses usually proceed. Right, and so the outline of the relationship between these two models, right, according to this approach, right, which really just in some sense synthesizes what's already out there in the literature, is that first, decoherence, or the interaction with the environment, defines a branching structure for the global quantum state. Right, then some interpretation-specific collapse mechanism explains how, and in specifically what sense, a particular branch is stochastically chosen as the outcome of the branching process in accordance with the Born rule. And then, right, so then we have, right, if once we have a unique branching structure and an interpretation-specific collapse mechanism, this defines a branch relative stochastic dynamics for the system. Right? And relative to which the state of the system is narrowly localized, right, say in a narrow wave packet or a coherent state. Right? So determinate localized subsystem evolutions are recovered as the stochastic evolution of the branch relative state of the system, which is a narrow wave packet. Right? And an open systems form of Ehrenfest theorem entails that stochastic branch relative trajectories approximate solutions to classical equations of motion on timescales over which the ensemble spreading of the system's reduced density matrix can be neglected. Right, so just a bit more technically, right, we can decompose the unitary evolution of the wave function into branches. Right? And I won't go into detail here, but basically these branch operators, C alpha 0 to alpha n, right, constitute the different branch states. Right? And these branches must satisfy the requirement of consistency. Right? However, it also should be noted that this requirement is a bit problematic because consistency does not uniquely constrain the branching structure. Right? And so given this branching structure defined by the unitary Schrodinger evolution, right, and some interpretation-specific collapse mechanism, right, we can define a branch relative stochastic evolution. Right, on average theory, right, all branches remain equivalent. On de Broglie-Bohm's theory, the configuration selects a particular branch. And on GRW theory, right, the stochastic dynamics, right, singles out a particular branch in a stochastic manner. And so assuming that all interpretations are empirically equivalent up to some small margin of error, right, the unitary Schrodinger evolution defines the set of possible determinate histories and their probabilities irrespective of the interpretation. Right, and so, right, so if one assumes that the reduced system dynamics obeys the Caldeira-Leggett equation, which is a very widely applicable equation to describe open subsystems, right, then that the reduced system dynamics, one can prove a form of Ehrenfest theorem for open systems, for open quantum systems. Right? And then if one restricts to reduced density matrices that are narrowly peaked in position, one can show that expectation values of the system approximately obey Newton's laws. Right? And that relative to a particular branch, right, the stochastic fluctuations, or the quantum fluctuations, will be very small around the classical trajectory. Right? So fitting this into the general picture that I've outlined before, right, so we have a function from the low-level state space to the classical phase space, right, which just consists of taking branch relative expectation values, right, of the system's position and of the system's momentum. And taking branch relative expectation values of position and momentum, right, defines a stochastic dynamics in classical phase space. Right? So the branch relative dynamics in the quantum Hilbert space induces through this function, right, and this W is just a normalization factor, right, induces through this function, right, a dynamics on the high-level state space, which under the assumption that the state satisfies certain constraints, right, which I won't go into detail, we can discuss in the question period. Right. So under the assumption that the state satisfies these constraints, the induced dynamics, the dynamics on the classical phase space induced by the quantum branch relative dynamics approximates the dynamics of the classical model. And so it is in this sense that the quantum model approximately instantiates, right, the classical dynamics. Right, so the picture, right, the physical picture we have here, right, is that all these kind of fanning out branches all correspond to particular branch relative trajectories in phase space, right, each trajectory associated with a particular branch. Right, through some interpretation-dependent collapse mechanism, a particular branch is selected in accordance with the Born rule that's represented by the dotted line, and the solid line is the actual classical trajectory. Right, and as long as this spreading is not too rapid, right, the induced quantum trajectory will approximate the classical trajectory. So here's just one example of this sort of general framework, but there are many others that I could provide you. So I just want to skip ahead, since I'm running out of time, to discuss the relationship between this concept of reduction and a certain concept of emergence and universality that's been introduced by Karen, right? So emergence is sometimes defined as failure of reduction, right? However, like Butterfield, right, Crowther 2015 argues for a concept of emergence defined independently of reduction in terms of novelty and autonomy. And the way Karen fleshes out the concepts of novelty and autonomy is in terms of universality and multiple realization. And reduction in the sense of domain subsumption is fully compatible with emergence in Crowther's sense. Right? So reduction understood as instantiation is completely compatible with multiple instantiation. Right? So reduction in the sense of domain subsumption only requires that there be some quantity in the low-level model that approximately instantiates, right, the high-level dynamics in cases where the high-level dynamics works. Right? That is perfectly consistent with the high-level dynamics being multiply instantiated within the low-level model. So showing that a particular high-level regularity is instantiated by some low-level description is a distinct task, right, from explaining universality or why we have multiple instantiation in certain cases. And both sorts of explanation or both sorts of account are necessary. Right? And so finally, I'll just finish up with a final point. Right? While a high-level model or theory, right, can be autonomous from a low-level theory in the sense of being unaffected by certain changes in details of the low-level description, right, if reduction in the sense of domain subsumption holds, right, then the regularities of the high-level model are instantiated only insofar as the low-level model dictates. Right? So there's still a sense in which even when one has multiple realization or universality and a certain sense of autonomy, right, the low-level model, if the sense of reduction holds, still dictates or circumscribes the cases, right, in which the high-level model offers an approximate description of the system itself. So there's a sense of autonomy that's compatible with the sense of subsumption or reduction. And I'll just finish here. Thanks.
So I have a few comments about realist assumption you had in your approach. So you defend the idea that reduction should be addressed not in a purely formal manner, but as an a posteriori relation, paying attention of the empirical domain where the scientific theory has been proved to be successful. So your approach needs some theory of confirmation, but it seems also that in your approach you need you have some implicit assumption of realism.
Yes.
And so my first question is about the status of this realist assumption. Can you just explain if you are committed to this assumption or if you can just drop it?
Well, so yeah, I think that's something that remains to be seen. I think we can proceed here in this way on the assumption of realism, the extent to which it can be expanded to, say, an empiricist view, I think is something that remains to be seen.
Okay. I have time for a few questions. Yes. Okay, so then if you are a realist, so if you have this assumption of realism, can you say if you are a realist about the models or if you are a realist about the theory itself?
A realist about the model within the domain where it applies. Right? So a model, in some sense, provides a mold of reality within some particular domain, right, or a particular set of degrees of freedom.
Yeah.
Right? So there will be parts of domains of the state space where the model doesn't dovetail with reality, and other parts where it does. Right? So for example, right, in Newtonian mechanics, right, if we take very momenta that are very large, in the state space, if we look at phase space points with momentum such as the velocity is much larger than the speed of light, right, then we're not realist about that part of the model. Right, but there will be certain solutions, right, or within a certain domain of the physical state space, or of the Newtonian state space, right, the solutions will approximate the actual behavior of the system.
Okay, but then do you have an internal constraint to know where you have to be realist about the model and where you have to drop that assumption?
It's an empirical constraint, but you just have to look.
Okay.
You have to see, right, where the model works and where it doesn't.
Okay, and then. How can we learn something about, if we are realist, how can you learn something about the ontology of the theory if you are only studying local models of the theory? And then what about cases where you have different theories of quantum gravity that might share the same models of this phenomena?
Right. So really, I mean, I guess the ontology here, the approach to ontology implicitly is a sort of structural realist approach, where, right? I mean, these models approximate the structure of the system itself.
But if
in a sort of an approximate and domain-specific way. So what the ontology is essentially the structure. Now, of course, that comes with it all the sort of questions that naturally arise with structural realism.
Yeah.
Right? So how do we distinguish between structure and ontology? Right? And so, I think it would be a fair accusation to say that I'm sort of sweeping some of these questions under the rug of structural realism or approximate truth.
Okay.
And just saying that, okay, I'm taking these positions, they have their difficulties, but I don't necessarily need to resolve all the difficulties of these positions in order to proceed on their assumptions.
But at the end, do you think that we will be able to learn something from your approach about the ontology of a theory of quantum gravity, even if we have no confirmation of phenomena
Right.
to quantum gravity?
Yeah, I mean, so I suppose what we could potentially learn is that if we have a model of quantum gravity, then within a specific region of the state space, right, we want, say, a particular function of the quantum gravity state space to approximately instantiate the constraints of the standard model.
Yeah.
Right, so the standard model dynamics. In one particular subset, we wanted to instantiate, right, the Einstein field equations in another subset of the quantum gravity state space, right, with a different function. Right? So the idea is basically just that we look for different domains of the quantum gravity state space, and we look for functions from that space to the standard model state space and to the GR state space, right, such that this instantiation occurs.
Okay. Thanks.
Good.
Thanks.
I have one general comment, and then some specific issue regarding the quantum mechanical example. The general comment is, I was surprised that you demanded that the low-level theory, or let's say the less precise theory, approximates the high-level theory to the same degree that that theory approximates or describes the system. Because if I take that view, then I would say, for instance, that Newtonian mechanics is not a good approximation to general relativity in the solar system, simply because Mercury's orbit is much better described by GR than what Newtonian approximation can approximate the GR description. So that issue of precision is
Yeah, so I think you inverted it when the low level. So the low level theory is the more fundamental theory. The high level theory, or the low level theory is the purportedly more general theory. The high level theory is the purportedly less general theory. So the way it would work in the context of general relativity and Newtonian gravity is that in all those cases where Newtonian gravity, with solutions to Newton's equations. Okay.
And the second question is the quantum mechanical example. And in that case, I have a sort of criticism, which is in the classical description, you were describing the system. And then in the quantum level, you decided to enlarge the system and describe system plus environment.
Yes.
So in some sense, you're not describing the same stuff, you're describing different.
Yes.
And the second issue is that you said, well, the trajectories should be approximated. But of course, when we go from quantum mechanics to classical theory, we need to choose which variables, which operators we are going to follow when we follow trajectories. And it may well be that the answers depend on how you do that. In particular, the coherence often does not do a good job in selecting a preferential basis, and we have multiplicity of choices. And it could well be that the theory is well approximated if I choose the basis or the context in one manner, and it's not at all when I choose the context in different.
Right. So this is. So I'll answer your second comment first. So we're actually. Sorry. actually, so let me start with the first. So I take your point there, right? So we've enlarged the system to the system plus environment. In practice, right, what we could do, right, is define reduced system dynamics, right? So we could trace out the environment, right? So one reason I didn't do that was just to illustrate the branching structure. But what we could do is look at the reduced density matrix evolution and then define a quantum unraveling, so which describes just the system itself. Right, so quantum unraveling basically just takes the reduced density matrix dynamics, right, and assigns a stochastic, right, wave packet dynamics associated with that. Right? And those two ways of describing the actual subsystem, right, can be derived from this more universal branching description. So we can have a reduction then, right, of the classical model to the sort of effective reduced system dynamics, and in particular to this quantum unraveling. Right.
Then
Yeah.
the choice of the particular unraveling will be part of your theory.
Yeah. So basically, the idea is that the operators that you measure, and this kind of gets to your second point, right, are determined by the dynamics of the interaction. Right. So it's not that we're free. Right. If we fixed our Hamiltonian. Right, so if we fix the environment Hamiltonian, the interaction Hamiltonian, the system Hamiltonian, then it's not as if we're free to just measure any operator we want, right? The operator that we're measuring is determined by the pointer basis.
So you're bringing up measuring.
Yeah.
You're bringing up a third system, the object that is going to use the measuring.
Well,
The observer that is going to produce. So you're,
I take that to be included in the environment, though. So the environment just consists of all degrees of freedom external.
Are we going to trace over the observer?
Yeah. So the environment.
We use the things that he decides to measure. We're going to trace it.
Yeah. So the idea is that the environment consists of all degrees of freedom external to the system itself. Right. That includes the observer. It includes the apparatus. Right. And so yes, when we're describing the effective subsystem dynamics, right, we're tracing over all of that.
So we never get information about what the observer actually decided to measure.
Well, if you look in the branch state, so if you look at the global unitary evolution, right, and you look at the individual branch states, right, then you will find an observer in each of those, right, a copy of an observer in each of those branch states, right, and that observer will measure an outcome for the system depending on which branch they're on. Yeah, I mean, so the observer and the apparatus here are really just being treated like physical systems like any other.
My question is not what the observer actually obtains as a result of the measurement, but what he decides to measure.
Right, but what he decides to measure requires an adjustment to the interaction Hamiltonian, right? So then we've changed our setup, right? So if the observer decides to measure something else, right, then our Hamiltonian has changed, and then we have to reperform the analysis of branching. Right, so it's not as if the,
Sure. Thank you.
Thanks.
This question might just end up be a request for you to fill in some information that I dismissed.
Yeah, sure.
That the reducing and reduced relationship is supposed to be asymmetric.
Yeah, it is asymmetric, yeah.
The conditions that we gave, I didn't hear the asymmetry. Can you
Yeah.
tell me where the asymmetry is?
Yeah, so the asymmetry lies in the fact that we have to have a function from the low-level state space to the high-level state space. The function need not be one-to-one, right? So,
Right, so it just needs to exist a function.
right, well, I mean, so the constraints on the function are, I mean, they come from how our models fit the system itself, in a sense, right? So the function is really supposed to identify, right, the physical fact of what we take to be the supervenience relationship between the degrees of freedom described in the high-level model and degrees of freedom described in the low-level model. And it's the fact that the function need not be one-to-one that really creates that asymmetry.
So we find a function
Yeah.
in primary analysis.
Yeah.
What if I find a function that works the other direction? I mean, presumably you need to rule that out in order to keep the asymmetry between the reduced and the reducing theory. There is no function that goes the other direction.
Well, I mean, if what we want to, I mean, in some sense, I mean, if the question that we're trying to answer, right, is what quantity in the low-level model, right, represents those degrees of freedom in the high-level model, right, in all cases and more, where the high-level model does, right, then in some sense, I guess I mean, you know, there could exist some function, but it's just, it seems to me that it doesn't necessarily serve to answer the question. I mean, what we need is really just we need to identify a quantity in the low-level model that approximately instantiates the high-level dynamics in those cases where the high-level dynamics works. And my suspicion, although I have to think more about it, is that it's, if such a function exists in the inverse direction, it doesn't necessarily have any bearing one way or another on that particular issue, as long as there exists a function, an appropriate function that identifies the instantiating.
Yes, I agree. If there does exist a function, it doesn't threaten the results of your first analysis. The question is, do you then, I'm just going to run your analysis with this new function. I'm going to take off the subscripts H and L because they, use my purity in terms of thinking about the system. I got this function. I'm just going to come up with the opposite result you did. When you were saying that the high level reduces to, or is reduced by the low level. In my description, it's just the other way around.
Yeah, but I think there it's kind of I think it's ignoring the physical system itself in a way, because there you're just considering a kind of formal connection just between the mathematical frameworks of the model, right? And what we want, right, is this particular mapping to reflect the manner in which, right, the degrees of freedom represented in the high-level model supervene on the degrees of freedom represented in the low-level model, right? And a function like the one you're talking about, right, wouldn't do that. I think. Thanks.
You might say it lacked physical salience.
Yeah.
So I had another sort of question of clarification, something sort of in the back of behind it. Sorry about this, I forgot my regular glasses in my room. And maybe you did say this, but you said again. So what exactly do you mean by the domain of the higher level theory? How is that sort of characterized in this story?
Right.
And what I have in the back of my mind is if there's a sort of normative component to reduction, if it's something we want. If the domain is all the things that we know the higher level theory gets right, then reduction seems like, domain subsumption seems like a pretty sensible kind of desideratum. But if it's everything the higher level theory actually gets right, whether we know it or not, then that might actually be too strong for something to demand of a theory.
Yeah, I think that's a very good question. I mean, it at least includes what we know that the high level theory gets right. But I think I would hope to be more ambitious and say that it really includes, right, if we can identify some notion of approximate truth, right, then whether something is approximately true is independent of whether or not we happen to know that it's approximately true, right? And I do want to include those cases as well.
I guess what I'm thinking is that there might be a lower level theory which is clearly better because it gets so much more right and gives you such more information about what's happening, paints a much clearer, more detailed picture of how the world is. But around the corners, there's some bits that the higher level theory gets right, but this lower level theory doesn't because, well, there's some even lower level theory that's going to do sort of even better.
Right.
So demanding that it gets, it's sort of, there's Kuhn in the back of my mind as well, but demanding sort of truth preservation and just simple expansion is kind of a strong and perhaps implausible demand in theories.
Yeah, so I suppose if there were I have to see an example of a case in which, right, I suppose you have Kuhn losses, right, but I don't know whether it was legitimate to regard the reduced theory as actually approximately true in those cases, that the Kuhn losses may not have really been Kuhn losses in a way. But yeah, I think this still permits a certain notion of partial reduction, even if there are such things as Kuhn losses. But I guess I'd have to see, a convincing example of a case in which the high-level model was approximately true in a robust sense, or in a sense that we would.
Mons theory.
Sorry.
Mons theory applied to the
Which theory?
Mons.
Oh, you mean modified Newtonian gravity? Yeah, I don't know too much about it, but I'd have to.
Very well with galactic dynamics, works in the solar system. It fails when you go to.
Well, then I would say it's approximately true in the cases where it tracks the degrees of freedom.
It's better than
Right, and so, I mean, in that case, I mean, it subsumes all the cases in which the Newtonian model works, right? So I mean, if it does, then you would have a reduction in this sense. And that the Mond theory is approximately true in a more encompassing and more precise way, right, than the Newtonian theory.
For the example to work, we'd like Mond to do something better than a sort of more fundamental theory
Okay.
that does.
Take Mond and GR. Mond together with GR. GR works fantastically well in the solar system. Mond. So, but the galactic dynamics, Mond works better than GR. You don't do that much.
Right, so then I would say that Mond does not reduce to GR. Yeah.
But that's okay, it just depends whether we actually want our theories to reduce them.
Yeah, and I just say, yeah, I mean, I think that's perfectly acceptable, yeah. Yeah, I mean, so as an abstract worry, I think these Kuhn losses, you know, if they really exist, or, you know, I mean, it is a worry, I just, yeah, I mean, I would need to see, yeah, a concrete example.
It's hard to come up with examples, I'm exactly thinking of examples
Yeah,
where
yeah.
it's right, but we don't know it's right.
Yeah,
And then you
yeah.
get the new theory, and then they're probably not the kind of cases where
Right, so it's difficult to,
be interested in applying things.
right, because our assessments of approximate truth are in some sense referenced to the newer theory, in a sense, yeah.
Last question for you. Yeah, actually, two small questions. The first question is you mentioned the criticism of the Bronstein Cube. One of the criticisms was that the limits come from you, and then there was another point you mentioned that if you are not very careful with the new limit, you may end up something else in the second. So my question is, what extent do you think those are independent criticisms, or they are just different ways?
Sorry, could you just say the two criticisms again?
Limits, the fact that limits come from you is something different.
Yeah, I mean, I'd say that the limits not commuting objection is kind of less fundamental than the worry, you know, well, what limits do we even need to take in the first place in order to satisfy this definition of reduction, right? So there's already a sort of vagueness, right, about which quantities need to be limits of which other ones, right? And it just happens that these limits don't commute if one adopts, makes some particular attempts, right, or makes some particular commitments as to which quantities need to be which limits, need to be limits of others. But I'd say that, you know, I mean, in some sense that objection is, right, diffused to a certain extent by the initial worry about vagueness, right? What needs to be a limit of what in order to satisfy this definition of reduction?
The second,
Yeah.
second point, the more general point about how we want your claim to be understood. That there is the feeling that something is very valuable about connection, really in terms of effective theory.
Sure.
So when you propose proxy perspective, you say that in some contexts that may be helpful. To what extent is that a suggestion to replace the paradigm, let's say? And to what extent it is just a suggestion to have an additional perspective on what's going on, while it may still be very helpful to look for effective.
So you're saying effective theories are kind of an instance of the limit approach in a way? Yeah, I mean, so I think that, I mean, it depends how you understand the limit approach, right? And because it's kind of a very vaguely defined sort of approach. It's just, I mean, I think that the thing that all kind of versions of this approach have in common is that somehow a limit is involved, right, in explaining why one theory works on the basis of the other. And I have no objection to using limits, right? I think that they're clearly essential in many cases, right, and particularly in effective field theory. So I didn't mean to suggest, right, that limits aren't important or crucial, right, but it's just a particular way of taking limits, say, in terms of these constants of nature, right, that's problematic, Right, so no, I mean, I think the whole analysis in terms of effective field theory is also in statistical mechanics, right, taking the thermodynamic limit, right, those are all absolutely essential, right, to reduction in this sense. And the way they come in a sense, although it wasn't apparent from what I said, is that, right, say, restricting to a particular domain of a state space, right, can correspond to taking a sort of limit, right? If we restrict to the domain of relativistic state space of low momentum states, right, in a sense that's taking a limit, right, because you're looking at all the states with momenta that are close to zero in a sense, right? So limits can come in a variety of ways, whether it's restricting to a particular domain or subset of the state space, or in a variety of other ways, right? But how limits come into reduction is actually way more varied and way more nuanced than the Bronstein cube suggests.
This example, this example brings again this issue of having the reduction dependent on other issues that have not been specified. When you say we look in special relativistic situations to things with low momentum. Okay, low momentum in which frame? You need to bring some other information that defines for you the preferred frame in which you're going to promote things with low momentum. Without that, this limit is not well defined.
Yes, no, I agree. And so, I mean, I think that basically you would assume the same frame between the classical, right, and so the classical state space and the quantum state space. So you fix your frame when you specify the state space, and you want to ensure that it's the same between both models, right? And then, right, the idea is that when you restrict to the low momentum region of the relativistic state space, right, you approximately satisfy the Newtonian equations of motion, right? But yeah, there is implicitly, in that particular case, a fixing of the frame that's common to both models.
Okay, thank you very much. Please.
Thank you.